and welcome to the 25th lecture. Last time we had started listing some examples arising from the regular value theorem. So I'll continue with that. And then we'll talk a bit about tangent spaces to the submanifolds that we obtain. So I had ended with the example of the set of orthogonal matrices, which is called the orthogonal group ONR, and this turned out to be a submanifold of MNR, which is essentially Rn squared, and its dimension is n into n minus 1 by 2. This was where we had stopped last time. Now there's one more interesting example that I would like to discuss in this, which arises from matrices. So let's see. So this was example number 3. Let SL and R be the set of n cross n matrices with determinant of A equal to 1. So let's prove that this is also a manifold. In this case, the function, so we would like to apply the regular value theorem, and the function for which this is the level set is clear from the definition, namely it is a determinant. So let us consider the determinant function from MNR to R. So let's give it a name, f of A equals det A. Claim. I'll make two claims. First thing is that in order to, so one would like to check the rank of the derivative of f at any point A in SL and R. Now I claim that so one would like to check that so the derivative has full rank. Well, in this case the target is R, so we just want to ensure that the derivative, so here I'll remark that, note that df at any point A would be a map from TA MNR to the tangent space of R at f of A, but we know that this is just R, and likewise since MNR is a vector space, we know that this is MNR itself. So dfa is just a map from MNR to R, and to say that this, so we would like to know whether this is surjective or not as a linear transformation from this vector space to this vector space. Well, since the target is R, surjectivity amounts to saying that this is the this is a non-zero linear transformation. I mean a linear transformation which is not identically zero. So surjectivity of dfa equivalent to dfa not equal to 0. So in other words, here not equal to in the sense of linear, as a linear map. Well, yeah, right. So that's all that one has to check. Now let's see. So IE, and this amounts to IE dfa of H is not equal to 0. Well, now 0 is a real number for some H in MNR. So I just have to find But I need a formula for DFA. Now, first claim is that DFI, I'll take A equals I. Notice that the identity matrix is an element of SLNR, trivially. And DFI as a map from DFI of H turns out to be just trace of H. Now, in order to show that the derivative at identity has full rank, as I have written in the right column here, it amounts to saying that I can find a single H for which this is not 0. And there are lots of choices for which, so you just have to find some matrix whose trace is not 0 and you'll be done. So if, for example, you can take H to be identity itself. H equal to I, DFI of H is not 0. So therefore, the derivative at identity has full rank. But what about other points? The second claim is that if I take any other point in SLNR, then rank of the derivative of f at that point is the same as the rank of DFI. If we have these two claims, then we would be done, because given 1 and 2, we see that SLNR is a submanifold of MNR of dimension. Remember that the dimension given by the regular value theorem is just the dimension of the domain minus the target. So dimension of domain is dimension of MNR, which is n squared, and target is 1, dimension n squared. So this immediately follows. Now let us see why 1 and 2 are true. So proof of 1 and 2. So let's start with 2. It's the easier one. Well, so I have to start with some A. Consider the map phi from MNR to MNR given by phi of x equals AX. So this is the same A that I'm starting with here, and I just multiply x with A. Okay, so now phi, note that f of phi of x is f of AX, determinant of AX is just determinant of x, since determinant of A is 1, which is the same as, well, it's f of x. So this tells us that f composed with phi is just f itself. If I take derivatives, right, before I take derivatives, let's observe that, note that phi is smooth, and bijective. Well, it's smooth simply because all it's that's happening is that I'm just multiplying x with a fixed matrix A. So if I look at the entries of phi, the n squared entries, component functions of phi, they are just linear combinations of entries of x. So phi is trivially smooth, and it's bijective because I can explicitly write down the inverse. In fact, the inverse is phi inverse of y is just A inverse of y. Maybe I should write this in a clearer way. So phi inverse of y is A inverse y, the inverse of the matrix multiplied by this. So we have an inverse, and again, for the same reason that phi was smooth, phi inverse is smooth as well. It's just multiplication by a fixed matrix, and the component functions of phi inverse are just linear functions of the input. Also, phi inverse I is smooth. So in short, phi is a diffeomorphism. Of MNR. So now let's go back to this equation here and take derivatives on both sides. Now that I know phi is smooth and so on, I take the derivative on both sides and use the chain rule. So I'll take the derivative of the right side at the point A. So rather at identity, at I. So f equals this. So df at identity is d of this at identity, and by chain rule this is df at phi of identity composed with d phi at identity. Well, phi of identity by definition of this map phi of identity is just A. So this is df A composed with d phi of identity. Now I don't need to compute d phi at identity. So all I need to know is that I already know that phi is a diffeomorphism, so that its derivative is an isomorphism at every point. In particular, df at dfi is an isomorphism. Since phi is a diffeomorphism, dfi is an isomorphism. And then I'm done, because my object of interest is the rank of, how to relate the rank of derivative of f at identity with derivative of f at some other point A. And these two are related by just this composing dfa with an isomorphism. When I do that, I don't change the rank. So the rank of this side, dfa composed with this, is the same as rank of dfa. And this equation tells us that that's the same as rank of dfi. So hence rank of dfi equal to rank of dfa. And as for the other thing, which is dfi, derivative of f at I of the determinant function, is just given by trace of h. This is the other claim. Now, there are a couple of ways of doing this. One is to use the exponential of matrices. Here I'll take a more straightforward approach. So we would like to claim, so i.e. limit h going to 0. So let's go back to the definition of derivative of h going to 0 of f of I plus h minus f of I minus dfi of h, which is trace h divided by norm h equal to 0. So this is what the definition tells us. Now let's calculate. Let's estimate f of I plus h. The second term here is f of I, which is just 1. F of I plus h is determinant of I plus h. If I write h as usual as h11, h1n, hn1, hnn, then this would be determinant of, I just add 1 on the diagonal, 1 plus hnn. The other entries are the same, h1n, h1n, hn1. Now the point is, I would like to, so when I expand the determinant, the plan is to expand the determinant along the first row. So let's take this first row and expand it along the, calculate the determinant by expansion along this. So I'll get, for instance, the first term will be 1 plus h11 times the minor corresponding to that would be this matrix. I want to isolate those terms which are linear in the HIJs. So I want to club all the terms in the expansion which have which are a product of more than one, product of at least 2 of the HIJs in one place, and those which have just, which are linear in HIJs in one place. So it's easy to check that the linearity part will come, it has to come from this term. All the other terms in the first minor as well as all the other things in the first row, everything else will contribute, will be a product of 2 of the HIJs. I'll just write that as small o of norm h squared, where small o of norm h squared is a term not a term, is a function of the Hij such that this function, when I divide by norm h squared, actually not norm h squared, norm h, since I've used the small o notation. And likewise here, the small o notation means that this divided by norm h goes to 0. So essentially I've clubbed, so these are things which involve, as I said, product of more than. Note that, so let me note that if I have two terms hij, hkl, then any such thing will go to 0 as h goes to 0. To see this, observe that this equal to 0. So the moment you have a product of two or more of the HIJs, I have this property, and well, that this is 0 is quite clear because Hij will be less than or equal to norm h, both Hij and HKL are less than or equal to norm h. So the product, when I take absolute value, in fact I can put absolute values here. So product HKL comma this, both of them are less than or equal to norm h. So the product will be less than or equal to norm h squared. So this entire thing less than or equal to norm h squared divided by norm h, and that will go to 0. Observe that. Since this happens, okay. So the the only term in the expansion of det of I plus h which will not be a product of more than one Hij arises from this, the first term here. But even that, there is only one term which is linear in the Hijs. Also, there is a term 1 coming from the product of all the ones, and then there is this term h and n, and the remaining terms again involve product of more one of the Hij. So I'll again put small o of norm h. So this, when I plug in these two things, one is this expression here, the second one is this, and let's plug both of these back into this main expression here. Oops. The main expression is this. So I plug this into that. So f of I plus h, first I write like this and put it here. The one, notice that, and then I use this one. So I get a 1, and then this is exactly trace h. So what I have here is 1 plus trace h plus small o of norm h. And so it essentially, and f of I is also 1. So that one cancels with the one coming from f of I plus h. And the trace h cancels with this trace h here. So I'm left with order of, so I have one small o of norm h coming from here and another one coming from this. So I can combine the two and get another small o of norm h, another function. So the limit of this will boil down to, so this will boil down to limit h going to 0 of small o of norm h. By the way, here I need not have used the norm sign since the target is real numbers, just absolute value would have been fine. But that's anyway, that's not so important. So limit of this divided by norm h is what I'm left with. And by definition of small o of norm h, this is 0. So that proves everything, that the derivative at identity is precisely trace. So now the next example I would like to discuss is something quite familiar, which is the graph of a smooth function. Fine. Let U contained in Rn be an open set and f from U to R be a smooth function. So the graph of f is the set S equal to set of all x comma f of x, and this x in U. So this I'm adding one extra component. X was already in Rn. X is in U, which is in Rn, and I'm putting one f of x. F of x is just a real number. So this is a subset of Rn cross R, which is Rn plus 1. So the graph is a subset of one higher Euclidean space of one higher dimension. And this is precisely what we deal with in one variable calculus, or for instance, where n equals 1. Now, so pictorially, U is some open set, and the graph, this is S. So at each point x, essentially one can think of it as the second coordinate as height over x. So at the point x, you go height f of x. You can go above if f of x is positive, or below if f of x is negative. Now I would like to say that the graph of a smooth function is always a submanifold. You don't need any condition on the derivative of f, that it has for f can be a constant, for instance. So, and in fact, one can directly show that this is a one can explicitly construct a chart, a single chart on S. But let's use the regular value theorem and see what that gives us. phi of x comma s is f of x minus s. And this is a function defined on U cross R, which is an open subset of Rn plus 1. So this is, in this picture, it's a sort of cylinder. U cross R would be a cylinder, solid cylinder over U cross R. So this, and on that open set, I'm defining this function. This is smooth then before smoothness, note that phi inverse 0 would be set of all points x comma s such that f of x equal to s. So in other words, the second coordinate is f of x, but that's precisely the graph of f. Yeah. So let me stop at this stage, and then in the next class I'll compute the derivative of this phi and show that the conditions for the regular value theorem are satisfied. So we'll stop here. Thank you.